Imagine a room the size of a football field filled not with athletes but with machines. The air is warm and carries the sweet, almost caramelized scent of boiling sugar. This isn't a kitchen, it's a symphony of stainless steel, moving belts, and precise temperatures. Here, sugar isn't measured in cups, but in multi-ton silo deliveries. Flavors aren't added with a dropper, but from industrial drums of concentrated essence. This is a hard candy mass production facility, a place where the simple childhood joys of lollipops and candy canes are born from a breathtaking scale of engineering, chemistry, and relentless automation. Today, we're pulling back the factory curtain to see how these iconic treats are made by the billions, transforming raw ingredients into wrap delights ready for stores around the world. The journey of every piece of hard candy, whether a simple fruit drop or an intricate candy cane, begins with the same sacred trinity: sugar, corn syrup, and water. But in a factory, these are not pantry ingredients. Granulated sugar arrives by the truckload, stored in massive silos that feed directly into the production line via pneumatic tubes. Corn syrup, a key ingredient that prevents sugar from crystallizing and gives the candy its smooth, glassy texture, is pumped from tanker deliveries into heated storage tanks to keep it fluid. The process starts in the cooking station. Precisely measured amounts of sugar, corn syrup, and water are mixed into a giant copper or stainless steel kettle. This mixture is then cooked under vacuum at extremely high temperatures, typically between 300 degrees and 320 degrees Fahrenheit, 149 to 160 degrees Celsius. Cooking under vacuum is crucial. It allows the sugar to reach the hard crack stage without burning or developing a dark color, resulting in that perfectly clear, glass-like base. The cooking is a masterclass in food science, removing almost all moisture to create a super-saturated sugar solution that will solidify into a stable, non-crystalline solid. Once the molten sugar mass, now called the candy base, reaches the exact temperature and consistency, it is poured from the kettle onto a large, water-cooled table, or, in more modern lines, fed into a continuous cooling belt. At this stage, it's a clear, incredibly hot, and viscous blob. It must be cooled rapidly but uniformly to a temperature where it can be handled, around 175 degrees Fahrenheit, 80 degrees Celsius, while still being pliable enough to knead. This is where color and flavor enter the scene. In traditional batch production, the large slab of candy is divided. For a single color candy like a lollipop, the entire batch might be tinted. For striped candies like candy canes or swirls, the batch is meticulously split and each portion is sent to a pulling machine or a series of dosers that inject precise streams of colored and flavored syrup. The next phase is one of the most iconic in candy making: pulling and kneading. Historically done by hand, this is now accomplished by massive mechanical arms or a series of rollers. The purpose of pulling is to incorporate air into the candy. This aerates it slightly, giving it a lighter mouthfeel and a bright, opaque, satiny appearance, as opposed to the clear glass of the initial cook. As the machine folds and stretches the hot candy, it changes from transparent to a soft, pearly sheen. Simultaneously, the pulling action ensures the flavor and color are distributed with flawless uniformity. There is zero margin for a streak of unflavored candy in the middle of a batch destined to become 100,000 cherry lollipops. For candy canes, this stage is critical for creating the classic white stripes. A portion of the batch is kept white and pulled to incorporate air. Another portion is dyed red or other colors. These two separate ropes, one white and aerated, one red and dense, are then combined in the forming stage. Now, the homogeneous, pulled candy mass is ready to be shaped. This is where the paths of lollipops and candy canes dramatically diverge, showcasing specialized engineering. For lollipops, the candy is fed into a machine called a batch roller. This machine takes the large mass and, through a series of graduated rollers, continuously shapes it into a long, thin, perfectly cylindrical rope called a batch. The diameter of this rope determines the size of the final lollipop. This candy rope then enters a forming press. Here, it passes between two metal rollers engraved with matching half-mold cavities. As the candy rope passes through, the rollers come together, stamping out individual candy shapes, circles, hearts, stars, and simultaneously embedding a stick into each one. The sticks, fed from a hopper, are perfectly timed to be inserted just as the candy is molded, where the residual heat seals it in place. The newly formed lollipops are then dropped onto a wide, slow-moving cooling conveyor. For candy canes, the process is a ballet of precision timing and temperature control. The separate ropes of red and white candy are fed into a combined forming machine. Guides and rollers lay the thinner white ropes onto the thicker red rope in the exact pattern to create the stripes. The composite rope then enters a twisting mechanism that spins it, creating the classic spiral stripe effect. Finally, it passes through a series of shaping rollers that taper one end to a point and gently curve the other to form the cane's hook. Unlike lollipops, canes have no stick inserted. Their shape alone is their structure. A high-speed cutter then slices the continuous rope into individual canes of exact length. The cutting must happen at the precise moment when the candy is cool enough to hold its shape, but still warm enough at the core to seal the cut without shattering. After forming, both lollipops and candy canes embark on a long journey down a cooling tunnel. This is a multi-tiered, temperature-controlled conveyor belt that can be 100 feet long or more. Cool air is gently blown over the candies as they travel for 20 to 30 minutes. This gradual, controlled cooling is essential to prevent thermal shock, which can cause cracking or internal stress, making the candy fragile. By the time they exit the tunnel, they are rock hard and at room temperature, ready for the final steps. The true marvel of a modern hard candy factory lies not in any single machine, but in the seamless integration of the entire system. A continuous, closed-loop process where raw materials enter at one end and finished, wrapped products exit at the other with minimal human touch. This level of automation is governed by a central supervisory control and data acquisition (SCADA) system. This computer network monitors every variable: the temperature in each cooking kettle, the viscosity of the candy mass at the pulling stage, the speed of the cooling conveyor, and the torque on the motors driving the forming rollers. If a sensor detects that the candy rope at the batch roller is half a degree too warm, the system can automatically slow down the preceding cooling belt or adjust the temperature of the rollers. This precision ensures not just quality, but remarkable consistency. A lollipop made on a Tuesday in July must be indistinguishable from one made on a Friday in December. This is only possible through this total environmental and mechanical control. The science behind the hard crack stage is more nuanced than simply reaching a high temperature. It's about managing the sugar's crystalline structure. Sucrose, the molecule in table sugar, naturally wants to form crystals. Think granulated sugar or rock candy. The factory's goal is to prevent this, creating an amorphous solid, a disordered, glass-like state. The corn syrup is the key weapon here. It contains glucose and other complex sugars that act as interfering agents. Their irregular molecular structures get in the way of the orderly sucrose molecules, preventing them from linking up into crystals. The cooking process must drive off almost all the water, reducing moisture content to well below 2%, to achieve this glass transition. The vacuum cooking is critical for two reasons. It lowers the boiling point of the solution, allowing it to reach the necessary sugar concentration without the scorching, burned sugar flavor of caramelization, and it removes water vapor more efficiently, preventing the candy from becoming sticky or grainy later. The factory is, in essence, creating edible glass. Flavor and color incorporation is a high-stakes game of precision chemistry. The flavors used are not simple extracts, but highly concentrated, heat-stable compounds designed to withstand the extreme temperatures of the candy mass without degrading or evaporating. They are often added via metered injection into the candy stream just after cooking, or mixed into the mass during the initial kneading. The timing is crucial. Add flavor too early and it cooks off. Add it too late and it won't distribute evenly. Colors face the same challenge. Liquid dyes would introduce unwanted moisture, causing localized crystallization and foggy spots in the candy. Therefore, factories use pigment dispersions or powdered lake colors that are specifically engineered for high-temperature sugar work. For candies with multiple colors, like ribbon candy or complex lollipop designs, the machinery becomes extraordinarily complex, with separate color feeders and laminating rollers that stack layers of different colored candy with geometric precision before the final forming cut. Quality control is relentless and multi-layered. Beyond the final optical scanners, there are checkpoints throughout. Inline sensors use near-infrared (NIR) spectroscopy to analyze the sugar syrup before cooking, ensuring the ratio of sucrose to corn syrup is exact. Metal detectors and X-ray machines scan the candy mass after pulling to find any minuscule foreign object that may have contaminated the batch. Moisture analyzers test random samples from the cooling line. A reading even slightly above spec means the entire batch might be pulled, as it will lead to sticky, unstable candy that could fuse together in the bag. There is also the human element. Quality assurance technicians perform routine break tests, snapping candies to listen for the clear, sharp crack that indicates proper texture and cooling. They also measure weight and dimensions with digital calipers because consistency is the brand's promise. Packaging engineering is a feat of materials science and high-speed mechanics. The wrapping film is not just plastic. It is a multi-layer laminate designed for specific properties. The inner layer is often a polypropylene that doesn't adhere to the candy's surface. The outer layer is printable and provides a barrier against moisture and odors. For Lollipops, the twist wrap machines must operate at speeds of hundreds, even thousands of pieces per minute. Each machine precisely cuts a small square of film, wraps it around the candy head, and twists the two ends with a perfect, consistent tightness, all while the lollipop is moving on a conveyor. For candy canes, the challenge is wrapping a curved, fragile object without breaking it. The machines use forming shoulders and gentle belts to guide the cane into the wrapper, which is then sealed with a heated jaw that melts the plastic layers together without applying crushing pressure. Finally, the environmental and sustainability considerations of such a plant are immense. The primary byproduct is heat, massive amounts of it. Modern factories recapture this thermal energy from cooling tunnels and cooking kettles to preheat incoming water or sugar syrup, drastically reducing their natural gas or steam consumption. Sugar dust, a major explosion hazard, is managed by sophisticated air filtration and vacuum collection systems that capture dust at every transfer point. Water usage is a critical concern, particularly in the cleaning of equipment. Many plants now use clean-in-place (CIP) systems that automatically circulate cleaning and sanitizing solutions through the pipes and tanks without disassembly, using less water and chemicals. Waste candy, from misshapen pieces, trimmings, or test batches, is almost never thrown away. It is collected, crushed, and remelted into the cooking process as rework, a practice that requires careful calculation to maintain the integrity of the sugar matrix, but is essential for cost efficiency and waste reduction. From the molecular interference of corn syrup to the robotic precision of the palletizer, the mass production of hard candy is a testament to applied science. It transforms a simple concept, boiled sugar, into a logistical and engineering symphony. It demonstrates how a desire for sweetness and joy, when scaled to a global demand, necessitates a factory that is part kitchen, part chemistry lab, and part supercomputer, all working in harmony to produce a perfect, shiny piece of childhood, one after another, forever. The last act is packaging. For Lollipops, this often involves first wrapping the candy head in a thin printed cellophane or polypropylene wrapper using high-speed twist wrapping machines. The stick is left exposed. They are then counted and inserted into bags or boxes. Candy canes are typically wrapped whole in printed plastic sleeves, which are heat-sealed at both ends. Modern optical sensors check for defects in color, shape, or wrapping. Any misshapen, broken, or poorly wrapped candy is automatically rejected by puffs of air and recycled, often melted down to be recooked. The perfect candies are then collated, boxed, and palletized by robots, ready for distribution. From silo to store shelf, the mass production of hard candy is a mesmerizing dance of chemistry, physics, and mechanical engineering. It takes a childhood treat and scales its creation to an almost unimaginable level, ensuring that every lollipop is as shiny and flavorful as the last, and every candy cane has its perfect curve and stripe. It's a world where sweetness meets science, and the result is a little piece of consistent, delicious magic made millions of times over.